Okay, let's talk about a specific example of the integrated rate law called a half-life. So a half-life is very useful in all different types of science, but really what a half-life is it's an amount of time, half-life, an amount of time that it takes for an initial concentration of a reactant to decrease by half. So we use half-lives for a lot of things in chemistry and science. It's especially important in like nuclear medicine, where if somebody is given something radioactive for some sort of imaging or some sort of medical treatment, we know the half-life of that radioactivity, so we can know the amount of time that that isotope or drug is going to be radioactive in a patient. We also use half-life for things like carbon dating. We use half-lives for a lot of different processes. So the half-life is just a special case of the integrated rate law where the initial concentration is 1 and the concentration at that time is 0.5. So for any of these, you could just substitute in the initial concentration is 1 and then the final concentration is 0.5, and then you would solve for T. Remember, the half-life is a time. It's the amount of time it takes for the initial concentration to decrease by half. So if you were given an initial concentration of 6, and you wanted to know what was the half-life, you would put the final concentration as 3. Because as long as the relationship between the initial concentration and the concentration at some time, as long as this relationship is 1/2, then you will be able to solve for the half-life. So there are equations that have manipulated these integrated rate laws to solve for the half-life. What I think makes more sense, you can obviously use whichever version that you would like, but what I think makes more sense is if you just use the initial concentration as 1 and then the concentration at that time as 1/2, then you can always solve for the half-life, and it's one less set of equations that you're looking around for. So let's look at an example. So here is an example. It says ammonium nitrate is unstable because the ammonium ion reacts with the nitrate ion to produce nitrogen. So here is the equation. Okay, it says in solution, that is 10 molar ammonium. The reaction is first order in the nitrate ion at low concentrations, and the rate constant is 3.0 times 10 to the thirds, 1/seconds. So this is a little bit tricky because it tells you that the initial concentration of ammonia, I'm going to write out the whole question just so you can see it. In a solution that is 10.0 molar ammonium, the reaction is first order in the nitrate ion. And the rate constant equals 3.0 times 10 to the third 1/seconds. And it says, what is the half-life of this reaction? Which is the same thing as asking, how much time will it take for the concentration of the nitrite ion to decrease by half? So this is kind of a tricky question because this question starts out by telling us the concentration of the ammonium ion. But that doesn't mean anything to us because this question is asking about the nitrite ion. It says the nitrite ion. It says this reaction is first order in the nitrite ion. So we don't care about what's happening with the ammonium ion. We only care about what's happening with the nitrite ion because the nitrite ion is what they tell us the information about the kinetics for. They say this reaction is first order in the nitrite ion and the rate constant is 3.0 times 10 to the third, 1 over seconds. That's 10 to the third and then this is 1 over seconds. It's not 10 to the 31st. It's 10 to the third. And it says, what is the half-life of this reaction? So this is where it could become a little bit confusing because you might think the initial concentration that you would use in your formula is 10. And it's not because 10 is not the concentration of the nitrate ion. They don't tell you what the concentration of the nitrite ion is, and you don't need to know because you just need to know that it's going to decrease by half. So you could use 1 and 0.5. You could use 6 and 3. You could use 30 and 15. It doesn't matter what those concentrations are. It only matters that it decreases by half. So again, let's look at my integrated rate law. It's first order like our other one. So all that matters is that this relationship is this is half of this. So I'm going to write that out. Here is my integrated rate law for a first order reaction. It is the natural log of the concentration of my reactant at some time equals the concentration of my reactant initially equals negative K times T. So again, because this is the half-life, that means the concentration of A at some time is going to be 1/2 of whatever the initial concentration was. So I'm just going to say that the initial concentration is 1, and then the concentration at some time is 0.5. And then I'm going to solve for T. The time is the half-life. And then K was given to us in the problem as 3.0 times 10 to the third, 1 over seconds. So let's write that out. And then I'm going to put in here, T is 0.5, this is 1. So I'm going to take the natural log of 1, but I'll write it all out for us. Natural log of 0.5 over 1 equals negative 3.0 times 10 to the negative third, 1 over seconds, times time. So I'm going to take the natural log of 0.5 over 1, which is 0.5. So I'm going to say natural log of 0.5 is negative 0.693. So I'm going to say negative 0.693 equals negative 3.0 times 10 to the negative third, 1 over seconds, times T. I'm going to divide both sides by negative 3.0 times 10 to the negative third, 1 over seconds, negative 3.0 times 10 to the negative third, 1 over seconds. The answer is going to be T equals, this will be on the top now, negative 0.693 divided by negative 3.0 times 10 to the negative third. You get something like 231 what? Seconds. Now, it doesn't ask for a specific time. It just says, what is the half-life? So this answer should have two significant figures because this number has two significant figures. So I would say 230 seconds. Or you could go ahead and turn it into minutes. You could say it would be about 3.9 minutes. Or you could convert it into hours. You could do anything. You can use any unit of time. Most of the time we use seconds. That's by far the most common unit of time when we're talking about half-lives. Most of these reactions happen really quickly. This is not a very quick reaction. For it to decrease by half in almost 4 minutes, when the one that we did the other day decreased by 10,000%, 10,000-fold in 1 second. So it's all relative to different types of reactions. This is an example of a half-life. So there are special half-life equations that are derived for you in your textbook and in the slides. You can always just say the initial concentration is whatever, and then the concentration at that time is half of it. So you can do whatever you want to solve for half-life. But again, the half-life is an amount of time that it takes for the initial concentration of a reactant to decrease by half.